Hello everybody, my name is Georgios Katsikas and I'm going to tell you what you need to know about Smart Network Interface cards. This is a joint work with Barbette, Chiesa, Dejan Kostic and Gerald Maguire from KTH. With edge computing and the advent of cloud-native technologies, modern applications are highly disaggregated into microservices connected over the network. To provide high-performance cloud-native applications, it is essential to offload part of the application logic to the network. The main candidates for application offloading are today's network interface cards, or shortly NICs. The reality today is that NICs operate at the speed of multi-hundred gigabits per second. However, the available time to process small packets at 100 gigabits per second is only a few nanoseconds per packet. So in this paper, we question whether today's NICs are ready to sustain both high-speed packet processing and at the same time processing parts of the application logic as per the latest trends. At this point, let's quickly step back to see how NICs perform traffic processing. Modern NICs typically consist of a pipeline of match action tables similar to an SDN switch. Packets arriving at a port get classified by a set of match filters, and then one or more actions are applied to each packet before they leave the NIC for further processing. Using jump instructions, it is also possible to traverse multiple tables in the pipeline, and this offers additional processing capabilities which can be spread across various tables. In this context, we believe that it's worth studying the performance of NIC classifiers as they are key parts of today's internet services. In this study, we focus on widely deployed packet classification operations, and we investigate whether this performance is affected by runtime modifications of the packet classifier while the NIC is processing traffic. Overall, we attempt to answer the following research questions. First, does the number of rules or tables affect the NIC performance? Second, is the NIC performance affected by updates to the classifier? Third, is the performance of rule insertion or deletion operations similar across all types of rules? And finally, how much time does it take to update an existing rule? In the interest of time, we will address only two of these questions in this talk. Let's now proceed to the performance evaluation. We use a testbed with two servers connected back to back. One server acts as a traffic generator and receiver, while the other server is a device under test. Each server is equipped with a 100 gigabit Ethernet NVIDIA Mellanox Connect X5 NIC. This NIC is used to conduct all the experiments shown in the paper. However, we have made additional results available by reproducing all the experiments with 3 additional NVIDIA Mellanox NICs, ranging from 100 to 200 gigabits per second speeds. We begin our evaluation with scenario number 1. In this scenario, the traffic generator sends traffic towards the device under test, which runs a simple forwarding network function on CPU core 0. This network function receives incoming packets from the NIC. After these packets get classified by a set of rules pre-installed across one or more NIC tables, in this case tables 1 to 16. Then the network function forwards the traffic back to the origin server. Each rule set in this experiment contains 1 to 4 million rules. We inject MTU-sized UDP packets at the maximum speed of the NIC. In each experiment, only one rule in each rule set matches the entire traffic, and we measure throughput and end-to-end latency. First, we measure the throughput of the forwarding network function shown on the y-axis when an increasing number of rules is installed in table 1, as shown on the x-axis. Using a single table to install the rules allows the network function to achieve high performance, as it can operate at the speed of the NIC even with 2 million rules in the classifier. Then we start spreading the rules across an increasing number of tables. With 2 tables, there is a negligible throughput degradation when using very large rule sets. This performance degradation, though, becomes more and more tense as we increase the number of tables to 4, 8, and finally 16. In this latter case, the forwarding network function cannot achieve more than 20 gigabits per second, which is more than 7 times lower than the maximum attainable throughput. Looking at the latency perspective of this experiment, we see a similar behavior. The performance of the network function is predictable when using only one table. However, using 16 tables results in up to a 10-fold latency increase. In this scenario, we found that spreading rules across more than 2 tables incurs a substantial performance penalty. Specifically, using 16 tables, throughput decreases from 100 to only 13 gigabits per second, while the end-to-end latency increases by an order of magnitude. Let's now move on to the second scenario. In this scenario, a DPDK-based rule generator pre-installs an increasing number of rules between 100,000 and 4 million in table 1 and then updates these rules while measuring and reporting the update time. The rules being installed are exact matches, and we measure 2 cases. First is the standard rule update using DPDK, which involves an insertion of a new rule followed by a deletion of the old one. A direct rule update method is the second case, which we implemented in the Mellanox DPDK driver. The y-axis shows the rule update performance in thousands of rules per second. The standard DPDK API achieves around 300,000 rule updates per second on average, as shown by the black squares. In contrast, our direct rule update mechanism performs up to 80% faster, achieving more than 600,000 rule updates per second in some cases, as shown by the blue stars. In this scenario, we found that standard DPDK rule updates are non-atomic, thus slow. To solve this problem, we implemented a dedicated update API, which achieves up to 80% higher performance. Due to lack of time, we have summarized some additional findings of this work, which you may find in our paper. First, batch or periodic rule updates cause substantial throughput degradation while the NIC is processing traffic. And second, some rule types are installed more quickly than others. We strongly encourage the audience to take a look at our paper for more details. To conclude this talk, today's NIC classifiers achieve high performance, but not under all circumstances. We uncover limitations related to where or what rules are being installed. Also, updating the NIC classifier while the NIC is processing traffic results in substantial performance degradation. Finally, we propose a new direct rule update API to provide faster rule updates. Feel free to check out our paper along with open source code and results available. Thank you very much for your attention.